Good morning and welcome. My name is Clay, and I am here to tell you about the transition recovery attack on embedded state machines. So, effectively, what this study is meant to show is given a finite state machine executing on a embedded device, we hope to be able to say some things about that execution, about that particular state machine. So, effectively, we are going to apply the principles of differential power analysis to try to detect the state machines and possibly differentiate between the individual states as well. So our primary focus on this was to apply the k nearest neighbors algorithm to accomplish these goals. So again, effectively what we would like to do is take a deterministic finite automata, write it up in C, so have a C version of it, and then using a device such as the chip whisperer framework, can we run enough iterations and generate enough power traces to be able to identify some things about that state machine and use this clustering algorithm to further that goal. So roughly what this looked like then, for the two states, we wanted things that were common-ish computational models that are things that are typically like used in this environment, so this low power environment, that are still separate enough that we could make sure that what we're seeing was in fact what we had hoped to find and not just some sort of coincidence. So in studies such as this, because we are controlling the inputs, we are controlling the state machine, and we are effectively like viewing all of the information, we try to craft these in such a way that we aren't deceiving ourselves. So to help accomplish that then, we designed a state machine with two states, the first of which uses the fast inverse square root function, which effectively all that's trying to do is just make that calculation quickly. Now, it was done by the Quake developers years ago. If you have never seen it or read about it, it's a treat. It's really a neat trick, but it is also a computationally exhaustive thing if you do not do it this way. So it's very well defined. It's a very useful operation. The second state then, we effectively take the input and then we just do some bit shifting and we do some XORing. Very, very, very typical operations, just something starkly different from the previous ops. Okay? The other thing of note here is that we wanted a framework that was large enough that we could have a lot of data, but not small enough that we were kind of pigeonholing ourselves. So we used 8-bit input to do this, and we used all of the numbers from 0 to 255. So the results that we got, again, given each of the individual bit strings, we were able to cluster correctly 81.2% or 81.02% of the time. Now, that's a pretty good accuracy, but big picture, that means that out of the 256 possible classes, we are classifying them correct 80% of the time. That's pretty good. Now, to take it a little bit further, we could differentiate between the two individual states 100% of the time. What that tells us immediately, and that was the first thing that we checked, that the two operations that we have from the power dynamic side of things, those operations are distinct enough that we can tell the difference between them. And that ultimately showed us that like the assumptions that we made when we built this experiment out were sufficient to be able to move forward. Okay? So going forward then, the large goal here is to try to reduce the search space. We generated around 40 gigabytes of data and used that throughout this process. That's a large amount of data. If we hadn't had the computational resources that we did in the lab, we would not have been able to accomplish this task in nearly the amount of time that we did. Now, going forward, as we look at more complex state machines and more complex structures, this data is only going to grow. So one of the directions that we would like to take this study is to look at something like transfer learning and say, okay, can we take a subset of our data on a model that's pre-trained, whether we've built that model out or if someone else has, and apply it to this problem. Thank you for your time.